So we're going to continue using the limit and the summation to evaluate a couple of integrals. This one is 2x plus 2 integrated from 0 to 3. So every time we're trying to convert this into a limit, it should be a limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k. So f of x sub k ought to be 2x sub k plus 2 times delta x. Everybody good with that? That will not change. Every time you just replace your function in here with an x sub k and multiply it by a delta x, and the limit and the summation always stays the same. Everybody good there?
Yep.
All right. So then what we have to do is we have to figure out what delta x is, and we have to figure out what x sub k is. So delta x, as we talked about yesterday, delta x is always equal to b minus a over n, or in this case, just 3 over n. So everybody good with delta x being 3 over n?
Yeah.
And I think we talked about a formula for what x sub k will always be also. What is x sub k always going to equal?
A plus delta x times k.
So it's going to be a plus delta x times k. So in this case, that's just 3k over n. Everybody good there? So now we need to replace all of that in our limit and our summation. So this ought to become the limit as n approaches infinity of the sum from k equals 1 to n of 2 times 3k over n plus 2 all times delta x, which is 3 over n. Good or no?
Yeah.
All right. Our 2 times our 3k over n is 6k over n. And if we multiply 6k over n by 3 over n, what's that going to give us? That ought to be 18k over what? N squared. And then plus 6 over n. Everybody good there or no?
Yeah.
Okay. And 18 is a constant, n squared is a constant, and the 6 over n is a constant. And I know yesterday we were pulling out the constants and separating out this summation, but we don't actually have to write all that out if we don't want to. We know that the summation turns k into n times n plus 1 over 2. So this ought to just become 18 times n plus 1 over 2 n squared plus, and then this constant, I'm summing together n of these constants. So that ought to become 6n over n, right? It ought to become n of those constants. Everybody good with that or no?
Wait, why is it 6n over n?
So we're summing together a bunch of 6 over n's.
Oh, I see. Okay.
I'm going to write it out just in case anybody else is confused. But if I'm summing together 6 over n, I'm summing over 6 over n plus 6 over n plus 6 over n times. So that would be 6 over n times n. Everybody good with that now?
Yeah.
Okay, cool. So then now we just need to figure out what this limit is. The n over n should cancel. So this just becomes a limit as n approaches infinity of 18n squared plus 18n over 2n squared plus 6. And once again, this first piece is just a rational function. What is the limit of 18n squared plus 18n over 2n squared?
9.
So I have 9 plus 6, which gives us 15. Everybody good? Any questions on that?
Where did you get the plus 6 from? Plus 6n over n.
So we had the plus 6 over n, right?
Yeah.
Right. So we said that we're summing together in 6 over n's. 6 over n plus 6 over n plus 6 over n, and so on, n times. So if I add together n of these 6 over n's, that ought to be 6 over n times n. And so that's the 6n over n. The n's cancel, make it 6.
Okay.
Good or no?
Think, yeah.
Okay. And I know I was talking about this yesterday, but generally on the AP test, you're going to have an answer that is in one of these two forms. It'll generally be a multiple choice. They'll say convert this into a limit. And so it'll end up looking like one of these in the answer choices. But every once in a while, they'll ask you to actually evaluate it all the way out using the limit. So. All right, let's do another one. In fact, why don't you guys want to try and do this one on your own?
Yeah.
All right, so take a minute or two, see if you can work through this one on your own. I'll give you, I don't know, 2 or 3 minutes. All right, so first off, we should always have a limit as n approaches infinity. And we should have a sum from k equals 1 to n. And we should have 3 minus 2x of k times delta x. Everybody good with that?
Yeah.
Okay, and our delta x value should have been b minus a over n, or just 2 over n. And our x sub k should be a plus delta x times k. Everybody good with delta x and x sub k?
Yep.
Cool. All right, so then this becomes a limit as n approaches infinity of a sum from k equals 1 to n of 3 minus 2 times our x sub k, which is 2 plus 2k over n, times our delta x, which is 2 over n. And then we need to distribute all that through. So we've got the negative 2 times the 2 is a minus 4. So we got a 3 minus a 4 is a negative 1. And the negative 1 gets multiplied by the 2 over n. So that's negative 2 over n. And then we got the negative 2 times the 2k over n, which is negative 4k over n. And then that should become a minus 8k over n squared. Everybody good with that or no?
Wait, why is it minus?
Because I have a minus 2 right there. So I have 3
Oh,
minus 2
okay.
x sub k.
Got it.
Cool. Everybody good? Okay. So what does our negative 2 over n as we do the summation become? Becomes negative 2 over n times n. And the minus 8k over n squared becomes minus 8n times n plus 1 over 2n squared. Everybody good with that?
Yeah.
And then the first part of that is negative 2, and the second part of that, that's negative 8n squared over 2n squared, so that'd be minus 4, and we get negative 6. Any questions on that?
When you went from minus 8k over n squared to minus
8n times n plus 1 over 2n squared. Where did the 2n squared come from? Where did 2n squared?
I remember that k, the summation of k is n times n plus 1 over 2.
Oh, it's okay.
So that's where that 2 is from. Good? Yeah? All right.
Yeah.
Cool. All right, we're gonna do, those ones were all linear ones, the ones we've done so far, right? We're all linear. So we could have done those using geometry. So we'll do a couple quick ones where we wouldn't be able to use geometry for them. All right, we're gonna look at a parabola now. So what we're finding here is the area underneath the parabola y equals 3x squared from 0 to 2. So this ought to equal a limit as n approaches infinity of a sum from k equals 1 to n of 3x sub k squared delta x. With delta x equal to what?
2 over n.
2 over n. And x sub k equal to what?
2k over n.
2k over n. Everybody good so far? Everybody's doing all right with this?
Yeah.
All right. Promise we'll just do one more after this one and then we'll move on to some new stuff. So we replace the x sub k and we replace the delta x. And we end up with a limit as n approaches infinity of, let's see, this is a 4 times 2 is 8 times 3 is 24. K squared over n cubed. And now we have to, oops, I forgot my summation. Now we have to remember, I gave you guys a formula for k squared. What was the formula for k squared? Talked about that yesterday. N times n plus 1 times 2n plus 1 all over 6. So the k squared just gets replaced with that. This becomes a limit as n approaches infinity of 24n, n plus 1, 2n plus 1 over 6n cubed. And the degree of the numerator and the degree of the denominator are the same, correct? N times 2n is going to be an n cubed. So I have a 48n cubed over a 6n cubed, which is just 8 as we go to infinity. Good or no?
Good.
All right. One more. I'll let you guys start this one out on your own. So take a minute or so to see if you can figure this one out. Ready, go. So we've got a limit as n approaches infinity of a sum from k equals 1 to n of 1 minus 6x sub k squared times delta x, with delta x equal to 1 over n and x sub k equal to 1 plus k over n. Is that what everybody got?
Yeah.
Perfect. So then it's just a bunch of arithmetic here. Got 1 minus 6 times 1 plus k over n squared. And what's 1 plus k over n squared? That ought to be 1 plus 2k over n plus k squared over n squared. All times 1 over n. Everybody agree with that?
Yeah.
Yeah.
Cool. And so then hopefully I'm going to try and do as much of this distributing all in one step as we can. So the 1 minus the 6 is a negative 5. And so that'll be negative 5 over n when I multiply by 1 over n. Negative 6 times 2k over n ought to be minus 12k over n squared. And negative 6 times k squared over n squared ought to be minus 6k squared over n cubed. Everybody good with that?
Yeah.
All right. we know what the k and the k squared should equal, right? The k should be n times n plus 1 over 2, and the k squared should be n times n plus 1 times 2n plus 1 over 6. So this becomes the limit as n approaches infinity. The constant, there are n of those, so that becomes negative 5n over n minus 12n times n plus 1 over 2n squared minus 6 times n plus 1 times 2n plus 1 over 6n cubed. Everybody good there?
Yeah.
All right, and the limit of negative 5 n over n as n goes towards infinity is negative 5. This one is 12n squared over 2n squared, so that's just minus 6. And then this one is a minus 12n cubed over 6n cubed, so minus 2. And you should end up with negative 13. Hopefully you all got that. That looks good or no?
How can the area under the curve be negative?
Right,
I'm
so
just curious
good question.
conceptually.
And it's something we're going to talk a little bit more about. What an integral does is it figures out, like I said, the area between the curve and the x-axis. Effectively, that's what it does. But anytime the curve is below the x-axis, that value comes out to be a negative value. And so between 1 and 2, somewhere on that interval, or perhaps on the entire interval, that function is below the x-axis, and that's giving us a negative value there. So back when we were saying the integral finds the area under the curve, well, yeah, but also not exactly every time. We gotta do some extra work to be careful about when the function is above and when the function is below the x-axis, and we're going to talk about that as we move forward. The distinction between an integral and the exact area under the curve. Does that help? It's not a great answer for yet. For
Yeah,
right now.
yeah, it helps definitely.
Okay. Yeah. We're gonna talk a lot more about that, especially when we get into our applications of the integrals later on this year. So. Okay. Cool. Now, there's one other rule that we need to know for approximating these integrals, because sometimes we might be given just a graph of a function and not an equation to represent it, or we might be given a chart of values, just a bunch of data points to figure it out with. And so there's another rule called the trapezoidal rule, which is better than both the left and the right, and generally works out better than the midpoint approximation method as well. So the trapezoidal rule says, and don't worry, I promise we're going to get back to integrals eventually. The trapezoidal rule says, draw a bunch of trapezoids in here. And I'm not going to draw this one in the middle here because it ends up looking weird, but that's fine. Okay. Take the heights of the function at each of the values, and what we want to do is we want to draw a trapezoid so that one base is the height of the function, and then the other base is a different height of the function at a different x value. And then the height of the trapezoid is just the length of the subinterval. Everybody see that? So draw a bunch of trapezoids in here. Good or no?
Yeah.
Okay, cool. So the trapezoidal rule is generally more accurate than the midpoint. And we can see that we can find this area by doing this y value, the first y value, y naught, plus the second y value, y1, divided by 2 times the length of the subinterval, right? Times h, we'll call this h, the height of the trapezoid, right? That's the formula for the area of a trapezoid. Base 1 plus base 2 divided by 2 times height. And then base 1 plus base 2 divided by 2 times height. And then base 1 plus base 2 divided by 2 times height. Everybody good with that? Hopefully.
Yeah.
Okay. There are a couple of different ways to evaluate this out. One is just simply by doing that, finding the height of each subinterval, finding the average of the bases, multiplying it together, and then adding it to the next one, and the next one, and the next one. If the subintervals that you are given are not equal subintervals, you know how we've been doing some where the subintervals were not equal way back here, right? The subintervals weren't equal. So if I gave you a chart of values where the subintervals were not all 1 unit, or not all 2 units, or not all 3 units, okay, then the only thing you can do is find the area of each trapezoid and sum them together. But if the height of each trapezoid or the length of each subinterval is the same, so if h is the same for all of the intervals, I should be able to factor out the h and the 2, the 1/2 in front of this, and say that this approximation for the integral, or the approximation for the area under the curve, is h over 2 times y0 plus y1 plus y1 plus y2 plus the next one should have a y2 in it, right? And all of them should occur twice, except for the first one and the last one, because as I draw the trapezoids, base 1 plus base 2, right? Well, when I use this one once and I use this one once, but then as I move on to the next trapezoid, I use this one a second time, and then I use this one once. And the next trapezoid, I use this one a second time, and then use this one once. And so I use each height twice, except for the first height and the last height only get used in those endpoint trapezoids. And so we could rewrite this as h over 2 times y0 plus 2y1, right, plus 2y2, all the way up to 2y sub n minus 1 plus y sub n at the end, right? And here's that formula right here. This is only if the subintervals are of equal length. And then how do we find the h? Well, the h is the length of the subinterval, which ought to be b minus a over n. Good or no?
So are we gonna use this as well with like, are we gonna get a more general formula so we don't have to find y1, y2 and all the way up? Or
Well, no, I mean, this is the general formula, and you'll have to find, you know, y0 and y1 and y2 as you go through based on whatever function you're given.
okay.
Yeah. So let's see if we can do this. Let's see if we can use the trapezoidal rule with n equals 4 to estimate the integral from 1 to 2 of x squared dx. And so we should be able to find the exact value of that now by using this limit and this summation, but let's just approximate it using trapezoids. So if n equals 4, that means we have 4 subintervals. And what's the length of my interval? It's just from 1 to 2, right? So my h value ought to be b minus a over n, or 1/4. Everybody good with that? That's the h value in the trapezoidal rule?
Yeah.
Okay. So the trapezoidal rule then says 1/4 h divided by 2 times the first y value. So the first y value is the value at 1, and then I'm going to have a value at 1 1/4, 5/4, and I'm going to have values at 1 1/2, and I'm going to have a value at 1 3/4, and I'm going to have a value at 2, right? These are the beginning and end points of each of the intervals if I'm going from 1 to 2 with 4 subintervals. Would you all agree with that?
Yeah.
Okay. So what's the first y value? Well, the first y value, y0, is 1 squared. And the second one, we need to multiply by 2, and ought to be this one at this x value squared. And the next one will have a 2, and it'll be 3/2 squared, and the next one will have a 2, and it will be 7/4 squared, and then the last one will not have a 2 because I only use that x value of x equals 2 for one of the trapezoids. It ought to be 2 squared. Good or no?
Good.
Yep.
Cool. And that's all you got to do. And then you just go in and evaluate it. So 1/8 times, let's see, this is a 1 and this is a 4, so that's 5. Okay. And let's see, this is, what does that end up being? 25/16 times 2 is 25/8. And this one is 9/4 times 2, which is 9/2. And this one is 49/16 times 2, which is 49/8. And if you add all those together, I don't know, what does that come out to be? I think that comes out to be 150 over 8 inside of here, and then times the other 8 is 150 over 64. Somebody check my arithmetic on that, though.
Great.
Yeah, does that look good? I did my addition right. No good. Any questions or issues with that? That's the trapezoidal rule.
So is the reason we're squaring everything just because the integral has x squared in it?
Right, exactly. If that was x cubed, these would all be cubed. If that was sine x, then it would be sine of 1, sine of 5/4, sine of 3/2, and so on.
Okay.
Depends on whatever that function is, right? Because these are, according to our formula, right? These are the y values. And so we use whatever our function is to get those y values, right?
Okay. Thank you.
Good.
What happened to the 2 squared?
That was 4, and I just added it to the 1.
Oh, okay.
All right. Now, on to what we call the fundamental theorem of calculus. And this is exceptionally important. And hopefully we're going to get through enough of this that I can give you some work to practice with it this weekend. The fundamental theorem of calculus has 2 parts. The first part is called the antiderivative part. And it basically states that the integral, which I will also refer to as an antiderivative, is just the opposite operation of the derivative. So that if I have some function, capital F of x, that I say represents the integral from a to x, so from some constant to some variable of some other function, and I were to take the derivative of this capital F function, that is the integral of this other function, I just come out with the original function. It basically says the derivative of the integral of a function is that function. That's the fundamental theorem of calculus. So it's saying that if I take the integral of a function and then I take the derivative of that, I should come right back to where I originally started. Does that make sense?
Well, isn't a integral just a number? How do you get back to like the equation then for the derivative? Like say
Okay. Yes. So an integral, what we've been dealing with, an integral has just been a number. All of the integrals that we have dealt with are called definite integrals, and it was way back here. I mentioned it very briefly, right? These were called definite integrals. And the definite integral is something that is on an interval from a to b, right? So it has a lower limit and it has an upper limit, right? That are numeric values. And so we'll note that the difference now is that only the lower limit is a numeric value and the upper limit is a variable. And this is a variable and this is a constant. And so when we integrate a function or take the antiderivative of a function, and there is a variable in one of those limits, we end up getting a different function. We get another function there, which is a little bit hard to see at the moment because we haven't really done it yet. But that's just sort of the way it works. And I'll be able to explain it more as we get more into the other parts of the fundamental theorem of calculus. But when you take what we call an indefinite integral, so there's a distinction between a definite integral, which has an a and a b to it, of some function dx, and an indefinite integral, which is an integral of some function dx without limits on it. What the indefinite integral is doing, and that's what we're going to deal with a lot in the next week, is it's saying, take my function, let's say my function is x squared dx. And when I take the indefinite integral of that, I am getting a new function that represents the area under x squared. When I do it from a constant to a constant, from a to b, as a definite integral, I am getting a specific area. Let's say it's x squared, under x squared from a to b. So an integral can be one of two different things. It can be definite or indefinite. And a definite integral is a numeric value, and an indefinite integral is a function that represents the area underneath that curve from some value to some other value, if I were to decide to put in upper and lower limits to it. Does that make sense?
Yeah.
Hopefully so. So the way integrals and definite integrals work is the second part of the fundamental theorem of calculus. So the second part of the fundamental theorem of calculus, which I'll get to somewhere down here along the road, is that when you, and in fact, I'm just going to do it now, somewhere down here. It's got to be down here. No, where is it? Maybe it was just the next page. Oh, it was just the next page. The second part of the fundamental theorem of calculus, and I'm going to go back to the page previous in a second, says that a definite integral from a to b of some function is equal to this integral function, the one that we got when we took the integral, evaluated at b, minus the integral function evaluated at a. So the second part says, if I put limits on here, we're going to have some rules for finding integrals of a function, but for right now, we're just saying that a function that represents the integral of little f is capital F. So I evaluate capital F at b, and I evaluate capital F at a, and I find the difference between them. Does that sort of make sense or no?
When you're saying it's at b, is that the indefinite or?
So it's, maybe I don't understand what your question is, but when I say at b, it means that there's some function. So suppose that f of x equals, natural log of x. Okay. Well, there's some function, the integral of f of x equals natural log of x. There's some function that represents that. It happens to be the function x natural log of x minus x. And you don't need to know that, but it happens to be that the integral function of f of x equals natural log of x is capital F of x equals x natural log of x minus x. And the reason, well, there's multiple reasons why that is, but we would find that if the derivative and the antiderivative or the integral are inverse functions of each other, then when I take the derivative, and I'm going to do that right here, we're going to take the derivative of x natural log x minus x, it should end up.
I have not paid attention to my calculus class at all. I let out a little toot.
Focus on your calculus!
You're unmuted. Someone's unmuted.
I see that. That'll be fun in the recording later. Wonder who that was that is not paying attention in their calculus class. Oh well. So I lost my train of thought there. Okay, so we're saying that I'm telling you right off the bat that this function is the integral of natural log of x. So let's take x natural log of x minus x and take its derivative. So how do I take the derivative of x natural log of x? Using the product rule, right? X times 1 over x plus natural log of x times 1. And then the derivative of minus x is just minus 1. And what does that become? It becomes 1 plus ln x minus 1, or ln x. So almost every single function that exists, right, which we're supposed to get natural log of x, almost every single function that exists, almost, there is a specific function that represents the integral of that function, that represents the area underneath the curve of natural log of x. So if I wanted to find what's the area underneath natural log of x from, let's say, 1 to 2, I would plug in, I would find capital F of 2 and capital F of 1, where capital F was this function x natural log x minus x. And I would do 1 natural log 1 minus 1. And that would tell me what the area underneath the curve natural log of x is from 1 to 2. If I wanted to know what it was from 2 to 3, well, then I'd just plug in 3 and I'd plug in 2 and find the difference between them. Does that sort of make sense? Or no?
So what is the significance of the capital F? Like there's some lowercase f, there's some capital F. Does the capital like mean anything? Does it mean it's an integral or something?
Yes, the capital F means that this function is the integral of little f. That's all it means.
Okay, cool.
That's all that capital F. So that was back here somewhere. I said it. So capital F is the integral of little f. It's
Okay,
just some function that represents, since we don't know how to take integrals yet, we're just using generic terms. Capital F is the integral of little f. And so if we take the derivative of capital F, we should end up with little f. Right? If I take the derivative of capital F, and capital F was the integral of little f, so the derivative of the integral of little f is just little f. Is that a little bit better or no?
Wait, can you go back?
Sure.
Is f of t f of x or no?
It's not. It's just a different variable. People get confused on that one every year. Like almost everybody gets confused on that every year. We call f of t, we call t and the dt, we call them dummy variables because we prefer it to be an x, but then if I have an x up here, it starts to look confusing, basically, because there's, you know, it's supposed to be different variables when you go from one level of integration to the next. It's supposed to be a different variable. So like when you go from a function to its antiderivative, when you write it out formally, the original function should be in terms of t or any other variable for that matter. So that when you take the derivative, it comes out to be in this upper limit variable of x. That's not a very good explanation because there's not really a good explanation for it. There's no real reason for it to be a t. It could be any variable we wanted it to be, including x. But yeah. So I wanna try real quick. I don't know. I want to try real quick to do one problem with this and see if all of this can kind of be put together to a place where it makes sense to you. So what we want to do, and we'll do both of these ones, it shouldn't take more than a second here. What we want to do is we want to find the derivative of the integral from some constant, negative pi, to x of cosine of t dt. And since we don't know what the antiderivative of cosine is, you may know what it is, but that's fine. Since we don't technically know what it is, we're going to say that capital F of x is equal to the antiderivative of cosine of t. So that's what we're going to say. And so what does, without this derivative here, what does this integral mean? It means evaluate the antiderivative at the upper limit minus the antiderivative at the lower limit. Do you guys agree with that? That's the second part of the fundamental theorem of calculus.
Yeah.
Okay. So then, since the derivative of the antiderivative is just the function, the first half of this, the derivative of capital F, should just be little f of x. And what about the derivative of capital F of negative pi? Well, capital F is just some function. And if I evaluate it at negative pi, I get some number, don't I?
Yeah.
And what's some number's derivative?
0.
0.
0. So we just end up with little f of x or just cosine of x. So the whole point of this is that if I am taking the derivative of the antiderivative from some constant to a variable x, then the derivative of that is just the original function cosine of x. So by that same logic, what should the derivative of the integral from 0 to x of 1 over 1 plus t squared be? It should just be 1 over 1 plus x squared. Good or no?
So are you just saying that like the derivative undoes the integral there, and then
That's
you just are left?
Yep, that is exactly what we're saying. The derivative basically is the opposite operation of the integral. And so if I have the derivative of an integral from a constant to x, then the answer to that is just the original function in terms of x. We're going to have to talk more about this on Monday, but so don't stress. I'm not going to give you an assignment on this yet. We're going to talk more about this on Monday, and hopefully I can more clear and make you guys understand it better come Monday. You're going to have two things to do this weekend, though, before I let you go. One of them is going to be due tonight. It's going to be just some integrals that you're going to solve using the limit and the summation. And then the other will be a couple of practice problems with the trapezoidal rule. Won't be due until the end of the weekend. So that's what you're looking at for the next couple of days. Don't forget to donate to the drive. If you donate, either take a picture of yourself with your donation so that I can see how much you've donated and send it to me through email or Remind, or take a screenshot of your Venmo being sent with how much it was and make sure it shows the covers for whatever it was called. I have it written down, but now I moved the paper.
It's
Covers for live. Yeah, so if you do that, send it to me and I will respond to you and confirm that I have noted your donation. Other than that, have a good weekend. We're going to talk a lot more about this on Monday, and it will make a lot more sense once we get through it, I think, on Monday, once I draw some more pictures and ramble on a little bit. That's it for now. Have a lovely weekend. If you have questions, feel free to hang around.